Hi friends, welcome to the lecture of Advanced Discrete Mathematics. In last lecture, we have seen what are the generating functions and some examples depending on these generating functions. Now today we have to see how to solve the recurrence relation by using the generating functions. Okay, and this one is the last point of your that is combinatorics unit. Okay, solution of linear recurrence relation using generating functions. Okay, so we have to see how to solve the linear recurrence relation by using the generating function. So here examples, use the generating functions to solve the recurrence relations or the relations. First one, an which is equal to 3 times an minus 1 plus 2 where a naught is equal. So here we have to solve this recurrence relation by using the generating functions, and let us see. Let g of x, that is generating function gx, will be equal to summation n running from 0 to infinity an x raised to n is the generating function of sequence an of sequence an. Okay, here g of x is nothing but summation n running from 0 to infinity an x raised to n is the generating function of the sequence an. Okay, now multiplying this one, given that an is equal to 3 times an minus 1 plus 2. Now multiplying both sides of this reconciliation by x raised to n and summing from 1 to infinity, we get, therefore multiplying each term each term in the given relation given recurrence relation by x to the power n and summing from summing from 1 to infinity, we get. That is, here first we have to multiply this equation by x to the power n, and then we have to take sum from 1 to infinity. Okay, that is summation n running from 1 to infinity an x to the power n is equal to 3 into summation n running from 1 to infinity an minus 1 x to the power n plus 2 into summation n running from 1 to infinity x to the power n. Okay, now which implies this one, g of x is nothing but summation n running from 0 to infinity an x to the power n, and here this one is left hand side is nothing but summation n running from 1 to infinity an x raised to n. So this includes one term less than this g of x. Here a naught is not present since here n is running from 0 to infinity and here n is running from 1 to infinity. So in this there is one term less than this one. Which term? Which is a naught. A naught x raised to the x to the power 0. X to the power 0 is always 1. Therefore a naught is missing here. Therefore this one is actually nothing but g of x minus a naught, which is equal. This can be written. Here summation is running from 1 to infinity. Here first term will get a naught x to the power 1. So here let us take 3 common. Therefore we get 3x summation n running from 1 to infinity an minus 1 x to the power n minus 1 plus 2 into summation n running from 1 to infinity x to the power n, and we know that summation n running from 0 to infinity x to the power n is nothing but 1 upon 1 minus x. But here summation is running from 1 to infinity, and summation n running from 0 to infinity x to the power n is nothing but 1 upon 1 minus x, that is 1 plus x square plus up to so on. Okay. Okay. Now, so as here summation is running from 1 to infinity, therefore one term is less than this one. That is, one is not present in this one. Therefore, which is nothing but 2 into 1 upon 1 minus x, and one term is missing, which is minus 1. Okay. So, which is nothing but g of x minus a naught is equal to, and now summation here running from 1 to infinity a n minus 1 x to the power n minus 1, as n is running from 1 to infinity a naught x to the power 0. Next one is a1 x raised to 1, which is actually nothing but this one g of x. Okay, so which is nothing but 3x gx plus 2 into 1 upon 1 minus x minus 1, which is nothing but 1 minus 1 minus x, 1 minus 1 0, minus of minus x plus x, which is nothing but x upon 1 minus x. So which is actually nothing but 2x, oh sorry, 1 upon 1 minus x. Okay, which is best. Take the g of x term common, we get g of x into 1 minus 3x which is equal to a naught plus 2x upon 1 minus x. Therefore, which is nothing but 1 minus 3x gx is equal to a naught is 1 plus 3x upon 1 minus x, which is nothing but 1 minus x plus 2x. 1 minus x plus 2x is nothing but 1 plus x, which is equal to 1 plus x divided by 1 minus x, which implies gx is nothing but 1 plus x divided by 1 minus 3x into 1 minus x. Now here we have to use the partial fraction. By partial fraction, this can be written as 2 upon 1 minus 3x minus of 1 upon 1 minus x, which is from partial fraction, and we know that how to solve the partial fraction. Okay. 2 times, which is actually nothing but 2 minus 2x minus of 1 minus 3x divided by 1 minus x into 1 minus 3x. 2 minus 1, 1 minus 2x plus 3x plus x. Okay, so by partial fraction we get g of x is nothing but 2 upon 1 minus 3x minus of 1 upon 1 minus x. And we know that g of x, by this one, g of x is nothing but summation n running from 0 to infinity a n x raised to n, which is nothing but summation n running from 0 to infinity a n x raised to n, which is equal to, and we know that 1 upon 1 minus ax is nothing but summation n running from 0 to infinity a to the power n x raised to n, which is nothing but 2 into summation n running from 0 to infinity a is nothing but 3 to the power n x to the power n plus, sorry, minus summation n running from 0 to infinity x to the power n. 1 upon 1 minus x is nothing but summation n running from 0 to infinity x to the power n. So here we have to find out the sequence. Then sequence a n is nothing but a n equal to 2 times 2 into 3 to the power n minus 1 is the required solution. So in this way we can use the generating function to solve the given recurrence relation. Okay. So given sequence is nothing but 2 into 3 to the power n minus 1. A n is nothing but 2 into 3 to the power n minus 1. Okay. Now next example is second one, a n minus 9 a minus 1 plus 20 a minus 2 is equal to 0 whenever a not equal to minus 3 and a1 equal to minus 10. Okay. So next example is here we have to take the recurrence relation an minus 9 an minus 1 plus 20 an minus 2 is equal to 0 where a naught is nothing but minus 3 and a1 equal to minus 2. That is a naught and a1 are the given initial condition. Now here also let us find out its solution. Therefore, let us consider g of x equal to summation n running from 0 to infinity a n x to the power n is the generating function of sequence an, where an is given, sequence an is nothing but that is given representation will be an minus 9 an minus 1 plus 20 an minus 2 is equal to 0. Now again multiplying each term in the recurrence relation, multiplying each term of relation by x to the power n and summing from 2 to infinity, summing from 2 to infinity, we get here this one is nothing but summation n running from 2 to infinity an x to the power n minus of 9 into summation n running from 2 to infinity an minus 1 x to the power n plus 20 into summation n running from 2 to infinity an minus 2 x to the power n, and we will multiply this one by x to the power n which is 0 and its summation is again 0. Okay, so which is actually nothing but this one is summation n running from 2 to infinity a n x raised to power n, but gx is nothing but summation n running from 0 to infinity a n x raised to n. According to this one here, first two terms are missing, which are those terms which are a naught and a1 x. Therefore, this one is nothing but g of x minus a naught minus a1. Sorry, first two terms are nothing but gx minus a naught minus a1 of x. Okay, minus 980. Now this one. Summation n is running from 2 to infinity. Therefore, as n is running from 2 to infinity, let's say n equal to 2. This one is nothing but a1 x to the power. Then let us take x common, then which is nothing but summation n running from 2 to infinity n minus 1 x to the power n minus 1. And as n is equal to 2, then it is nothing but a1 x to the power 1. Therefore, first term is missing here of generating function gx. Therefore, it is nothing but 9x into g of x minus a naught, that is first term will be missing here, and plus 20 into, as summation is running from 2 to infinity, let's take x square common, then it is nothing but x square common, then it is a minus 2 x raised to n minus 2. As n equal to 2, then it is a naught x to the power 0. As n equal to 3, then it is nothing but a1 x to the power 1. Therefore, this is actually nothing but g of x, and which is equal to 0. Now we have to take the terms of g of x common, then we get gx into first here 1 minus 9x, 1 minus 9x, sorry, 1 minus 9x minus, sorry, 1 minus 9x into g of x minus a plus 20, yes, and so all the remaining terms on the right hand side. Here a naught plus a1x minus of 9x minus a naught plus, which is minus of 9 a naught x, a naught plus a1x minus 9 a naught x, which implies gx is equal to a naught plus a1x minus of 9 a naught x divided by 1 minus 9x plus 20 x, and which is a naught is minus 3, a1 is minus 10, minus of 10x minus a naught is minus 3 into minus 9 plus 27 years divided by this one is nothing but 1 minus 5 years into 1 minus 4 x is nothing but the 1 minus 9x plus 20x square minus 5x minus 4x minus 9x minus of 5x into minus of 4x plus 20x square 1 into 1 which is equal to minus of 3 minus 10x plus 27x plus 17x divided by 1 minus 5 years into 1 minus 4x. Now here again we have to use the partial fraction. By partial fraction, this can be written as 2 upon 1 minus 5 years minus of 5 upon 1 minus 4 years. Okay, this one is the g of x and which is from partial fraction. Okay, the partial fraction. Let us see this one is 2 minus 8x minus of 5. 2 minus 5 minus 3 minus of minus plus 25x plus 25 minus 8. 25 minus 8 plus 17. Okay, so now which is nothing but g of x is nothing but summation n running from 0 to infinity a n x to the power n and which is nothing but 2 into 1 upon 1 minus 5x is nothing but summation n running from 0 to infinity a to the power n x raised to n. Here a is nothing but 5, which is nothing but 5 to the power n x to the power n minus of 5 into summation n running from 0 to infinity. 1 minus 1 upon 1 minus 4x is nothing but 4 to the power n x raised to n, which implies a n equal to 2 into 5 raised to n minus of 5 into 4 raised to n is the required solution. Required solution. In this way, we can solve any problem of this type by using the generating functions. Now we have to see the next point, which is the counting problems and generating functions. That is, in this method, we have to see how to find out the coefficient of any power of years in the given polynomial. Okay, what are the counting problems and generating functions? In combinations, we have seen one rule, that is the combination of n objects taken are at a time with repetition at a time with repetition is nothing but is C n plus r minus 1 of r. That is, this can be written as n plus r minus 1 c r. Is nothing but the combination of n objects taken r at a time with repetition. Now, this same formula can be used to find out the coefficient of something. That is, suppose we have to find out the coefficient of x to the power r in the given polynomial, then we have to use the same formula, that is the coefficient of x to the power r in given polynomial is find out by using this formula, that is in polynomial is c n plus r minus 1 r. So here we have to use this one and find out the coefficient of x to the power r in any polynomial. Let us see some examples depending on this one. First one is find the coefficient of x to the power 10 in 1 plus x to the power 5 plus x to the power 10 plus up to so on, and it's now we have to find out the coefficient of x to the power 10 in this polynomial. This polynomial can be first written as let 1 plus x to the power 5 plus x to the power 10 plus x to the power 15 plus up to so on, and it's cube. It is nothing but, which is actually nothing but 1 minus x to the power 5 minus 1. Okay, 1 minus x, 1 upon 1 minus x, that is 1 minus x inverse is nothing but 1 plus x square plus x cube plus up to so on. So here x is nothing but x to the power 5, and this one is nothing but 1 plus x raised to 5 plus x to the power 5 square, which is 5 into 2 10 plus 5 x raised to 5 to the power 3, which is nothing but x to the power 15, and so on. So this one is nothing, this can be written in a closed form as 1 minus x to the power 5 raised to minus 1, and this 2 as it is. So this one is nothing but 1 minus x raised to 5 minus of 3, and actually this one is nothing but summation c n plus r minus 1 r x to the power, this polynomial is here, x is nothing but x raised to 5, and which is nothing but x to the power 5r, which is from the binomial coefficient. So this polynomial is actually nothing but this type, c n plus r minus 1 r x to the power 5r, but here n is nothing but 3, therefore which is nothing but summation c 3 plus r minus 1 of r x to the power 5r. So here if we run the r from 1 to infinity, then we get this given polynomial. Okay, now but here we have to find out the coefficient of x to the power 10, and here x to the 5 x to the power 5r. If we put r equal to 2, then we get here x to the power 10, and with r equal to 2, if we put this one, then from this formula we get the coefficient of x to the power 10. So for that we have to take 5r will be equal to 10. If we take 5r equal to 10, then we get the coefficient of given x to the power 10, which implies r is equal to 2. So if we put r equal to 2 in this given in this formula, then we get the coefficient of x to the power 10, which implies c n is 3 plus r minus 1 of r is equal to c 3 plus 2 minus of 1 of 2 is equal to, this can be written as c 3 plus 2 5 minus 1 4 2, and which is nothing but 4 factorial divided by 2 factorial into 2 factorial, and which is equal to, first 2 factorial is get cancelled, 3 into 4 divided by 2 2 into 2, sorry, which is equal to 2 into 6. Therefore the coefficient of x to the power 10 in this polynomial is 6. Okay, similarly find out the coefficient of x to the power 12 in polynomial x cube plus x raised to 4 plus x raised to 5 plus up to so on. Now we have to find out the coefficient of x to the power 12 in this polynomial. Now this polynomial can be written as let x cube plus x raised to 5, sorry, x raised to 4 plus x raised to 5 plus up to so on, and cube. Now take x cube common, this x cube raised to 3, which is nothing but x to the power 9, x to the power 9 into, if we take x cube common, then we have to divide this term in this polynomial will be x cube, therefore which is nothing but 1 plus x square plus up to so on, and actually this one is nothing but x to the power 9 into, this one is nothing but 1 plus x square plus x cube is nothing but 1 upon 1 minus x, that is 1 upon 1 minus x to the power 1 to the power 3, and which is nothing but 9 into 1 minus x to the power minus of 3. Now this can be written as, which is equal to 9 into, here when n is 3, which is nothing but c n plus r minus 1 r x to the power r only, since here x is given, therefore it is x to the power r. Okay, x to the power r. Now if we take this 9 inside, then we get summation n is 3 c 3 plus r minus 1 r x to the power r is already given, sorry, this one is x to the power 9, x to the power 9 into x to the power r is nothing but x to the power r plus 9. Okay, now here we have to find out the coefficient of x to the power 12. That is, here we have to take r plus 9 will be equal to 12. Then we get the value of r, which implies as we have to take r plus 9 will be equal to 10. There only we get the coefficient of x to the power 12 in given polynomial, which implies r plus 9 is equal to 12, which implies r is nothing but 3. As we put r equal to 3 and r equal to 3 in this given polynomial, then we get the coefficient of x to the power 12, which implies c n plus r minus 1 of r is equal to c. N is 3 plus r is also 3 minus 1 of r, which is nothing but 3 plus 3 6. 6 minus 1 5 of 3, and which is equal to 5 factorial divided by 3 factorial into 2 factorial. First 3 factorial is 2 cancel, 4 into 5 divided by 2 factorial. This one is 2 factorial into 2, 2 into 5, 3 into 4. Therefore, the coefficient of x to the power 12 in this polynomial is 10. In this way, we can find out the coefficient of any term in the given polynomial. Okay. There is one more example, which is, suppose there are young persons in a park. Okay, and each person shakes hand with everyone with everyone else exactly once. Else exactly once. Okay, for a recurrence relation, or a recurrence relation representing the number of handshakes occurred in the party occurred in the party also solve that recurrence relation. Also solve the recurrence relation. So here we have given that there are n persons in a party and each person shake hands with everyone else and exactly once. Okay, is exactly once. Then we have to form a recurrence relation which represents the number of handshakes occurred in the party, and also we have to solve that recurrence relation. Okay, let us consider, let Hn denotes the number of handshakes occurred in the park occurred in the park. Okay, this one Hn denotes the number of handshakes occurred in the party. Therefore, Hn is nothing but number of handshakes occur among the gathering of n minus 1 gates. There are n persons are here. Here, let us take. Instead of persons, let us take this one as a. Suppose there are n gates. Gates. Okay. Gates plus the number of handshakes made by the nth guest with n minus 1 number of gates. So actually Hn is nothing but the, here we denote Hn as a number of handshakes occurred in the party. Therefore Hn is nothing but the number of handshakes occurred among the gathering of n minus 1 gates plus the number of handshakes made by the nth guest with the remaining n minus 1 number of guests. So as Hn denotes the number of handshakes occurred in the party with n person there, and as number of handshakes occurred among the gathering of n minus 1 gates is nothing but this, from this one is nothing but Hn minus 1. Since Hn denotes the number of handshakes occurred in the party with n gates, therefore the number of handshakes occurred among the n minus 1 gates in party will be Hn minus 1 plus. Now, the nth person's handshake with remaining n minus 1 person, then the number of handshakes will be equal to n minus 1. Therefore, Hn equal to Hn minus 1 plus n minus 1 is the required recurrence relation, which is the required recurrence relation. Required recurrence relation. Okay, as this one is the required recurrence relation. As now here we have to also solve the given recurrence relation. And to solve this recurrence relation, we use the iteration method. As here, Hn is equal to Hn minus 1 plus n minus 1. Okay, which implies Hn minus 1 is nothing but Hn minus 2 plus n minus 2, which implies from this one Hn is nothing but put the value of Hn minus 1 in this one, which is equal to Hn minus 2 plus n minus 2 plus n minus 1. Okay, now this one is Hn minus 2. Now we have to find out the value of Hn minus 2. So Hn minus 2 is equal to Hn minus 3 plus n minus 3. Now put this one again this one, then which implies Hn is nothing but Hn minus 3 plus n minus 3 plus n minus 2 plus n minus 1. This is at the third step. Therefore, after kth term we get, which implies Hn is equal to Hn minus k plus n minus k plus n minus k minus 1 plus up to so on plus n minus 1. This is at the kth step. Therefore, put k equal to 2. K equal to n minus 2, which implies Hn is equal to h of n minus 2. N minus n minus 2, n minus n get cancel. Minus of minus 2 is 2 plus this one n minus of n minus 2, which is plus up to so on. Here is n minus 2 plus n minus 1. Okay, now put k equal to n minus 1. If we put k equal to n minus 1, we get Hn is equal to h1 plus 1 plus 2 plus up to so on plus n minus 2 plus n minus 1. But here, from this we know that Hn is equal to Hn minus 1 plus n minus 1. Therefore, given that there are n guests in the party and each person shake hands with everyone. Therefore, if we have to take one handshake, then we require at least 2 persons, and Hn denotes the number of handshakes occurred in the party. As handshake is occurred in between 2 persons, therefore H1 is equal to 0. That is, if there is only 1 person, then there is no handshake. Therefore, which implies this one is nothing but Hn is equal to H1 is 0, since we require at least 2 persons for the handshake. Therefore, 0 plus, And we know that 1 plus 2 plus 3 plus up to so on n is nothing but n into n plus 1 divided by that is 1 plus 2 plus 3 plus up to so on plus n is equal to n into n plus 1 divided by 2. But here the sum is going from 1 plus 2 plus 3 plus up to so on n minus 1. That is here value of n is nothing but n minus 1. Therefore, this one is nothing but n minus 1 into n minus 1 plus 1 divided by 2, which is from this formula. Since the sum of integers from 1 to n is nothing but n into n plus 1 upon 2, but here the sum is nothing from 1 to n minus 1. Therefore, it is nothing but n minus 1 into n minus 1 plus 1 divided by 2, which is equal to 0 plus that one, that is n minus 1. n minus 1 plus n, that is which is nothing but n into n minus 1 upon 2. So, which is the required solution. Okay, now there is one puzzle. We have to see that puzzle, that is Tower of Hanoi. What is its statement? Let us see first. The Tower of Hanoi is a puzzle consisting of three phases mounted on a board with disc of different diameters. Okay. Initially, they are placed as there are three planes. Initially, they are placed on peg 1 in order of size with largest is at bottom. Okay. These discs are to be these are to be transferred to the second peg with their relative positions unchanged. The rules of puzzle allow this to be moved one at a time. From one page to another as long as discs never placed never placed on the top of smaller one. So this one is the statement of our Tower of Hanoi. That is, this one is actually a puzzle, and this puzzle states that the Tower of Hanoi is a puzzle that it states that it consists of three pegs mounted on a board with discs of different diameters. That is, there are the three pegs and any number of discs of different diameters, and initially they are placed on a peg one. That is, suppose there are three pegs. Okay, great. This one is the first one. This one is the peg 1, that is peg 1, and if suppose there are here some discs, these are the discs and they are placed according to their size. Okay, suppose these are the four discs, and this one is the first peg, this one is the second peg which is named as A, and the third peg which is, take this one as a second peg. These are the three pegs in which one peg is denoted by this Roman symbol I. First, this one is A and this one is the second one. Now, in order of size, with the largest is at the bottom. Here, largest one is at the bottom. Okay. Now, these are to be transferred to the second peg. That is, this one is the first peg and this one is the second peg. Now, we have to transfer these pegs, these discs from first peg to second peg with their relative positions unchanged. That is, this position is not changed. That is, the here also we have to take the largest one is at the bottom. Similarly, going on. Okay. The rules of puzzle allow disc to be moved one at a time. That is, here we can move one disc at a time. We can't take two or more than two discs at a time. Here we have to move one disc at a time. At a time from one peg to another peg, as long as this never placed on the top of the smaller one. That is, larger disc is never on the top of the smaller disc, and we have to move all the discs from peg 1 to peg 2 in the that relative position. Okay, now we have to see its solution. This one is the first, as from the Tower of Hanoi statement, that is, this one is the initial position. Okay, this one is the initial position. Now, let us see its solution. Solution. Let there are n discs on peg 1. Okay, and Cn denotes the number of moves needed to move this from peg 1 to peg. Okay. So here, suppose there are n discs, and Cn denotes the number of moves which are needed to move the disc from peg 1 to peg 2. Okay. Now, if n is equal to 1, that is, there is only one disc, then we can simply take this disc from this one to this one, and here we get the required solution of that given Tower of Hanoi. That is, if n equal to 1, that is, there is only one disc, then we can simply transfer that one disc from peg 1 to peg 2, and we get the required solution. If n is greater than 1, that is, the number of discs are 2 or more than 2, then if n is greater than 1, then Cn minus 1 moves required to move n minus 1 this from peg 1 to peg A. This one is the peg A. If suppose there are two or more than two disks, then we according to this statement, Cn denotes the number of moves needed to move this from peg 1 to peg 2. Similarly, if there are two or more than two disks, then Cn minus 1 moves required to transfer the disk from peg 1 to peg A. These are this for the n minus 1 pegs, and during the move, the largest disk in peg 1 stays fixed. Stays fixed. Okay, if suppose there are n disks, therefore Cn minus 1 moves required to transfer these disks from peg 1 to peg E, and this one is the largest disk, and this one is the as it is in peg 1. Since we have to move all the disks from peg 1 to peg 2, now we can simply take one move to move this the largest disk from one peg to peg 1 to peg 2. So here only one move is required to move a largest disk from peg 1 to peg 2. Okay, simply here we require only one move to transfer this disk from peg 1 to peg 2. Now here we get this one is at here, this one is the largest one. Now here on peg A there are n minus 1 disk, and similarly we can use Cn minus 1 moves to transfer the n minus 1 disk from peg A to peg 2. So again the n minus 1 disk on peg A can be moved moves on peg 2 by using the Cn minus 1 moves. Okay, so and these Cn minus 1 moves are occurred according to their relative position. Therefore, as we here take the Cn denotes the number of moves needed to move the disk from peg 1 to peg 2. Therefore, for calculating the Cn, first we have taken Cn minus 1 moves to move the disk from peg 1 to peg A. That is nothing but Cn minus 1 plus, and we use one move that is for the largest disk which is moving from peg 1 to peg 2 plus 1 plus, and similar, and finally we have using Cn minus 1 moves to move the disk from peg A to peg 2 plus Cn minus 1 where n is greater than 1, which is equal to Cn minus 1 plus Cn minus 1 is 2 Cn minus 1 plus 1 where n is greater than 1, and the initial condition is nothing but initial condition, that is if we get only n equal to 1, then we require there is only one move, that is C1 is equal to 1. Therefore Cn equal to 2 times Cn minus 1 plus 1 where n is greater than 1 and C1 1 equal to 1 is the required recurrence relation for the Tower of Hanoi. And as this one is, therefore Cn is equal to 2 times Cn minus 1 plus 1 where n is greater than 1 and C1 is equal to 1. Okay, so which is the required recurrence relation. Now after that, after we moving the n minus 1 this from peg 1 to peg A, we get this one is the peg 1, this one is the peg A, and here we get some Here is peak. Okay, and this one is the position after moving the n minus 1 disk from peak 1 to peak. Okay, so in this way we can use the method of Tower of Hanoi. So here we complete our fourth unit, that is combinatorics. So here we complete our syllabus of advanced discrete mathematics. Okay, thank you for watching the lecture.